So, we know that acceleration is the rate of change of velocity, which is the same as saying it's the change in velocity with respect to time. So that means we can write it as a equals dv over dt, the change in velocity with respect to time. So if we multiply both sides by dt, we get a dt equals dv. So this is a differential equation. We can integrate both sides. So we get the integral of a dt. We're going to evaluate this from 0, the initial time is 0, up until some time t. That's going to be equal to the integral from the initial velocity we call u to the final velocity we call v of dv. So now we just integrate. So we're going to assume that acceleration is constant because that's what we do in the first iteration. So that gives us at evaluated from 0 to t equals the derivative of dv is just v from u to v. So now we can just sub in our limits of integration. We get at minus a multiplied by 0 equals v minus u, which gives us that at equals v minus u. We're going to try and solve for v, so we're going to add u to both sides, giving us that v equals u plus at. And that is the first equation of motion. So to get our second equation of motion, we can define velocity similarly to how we defined acceleration. So we can define it as velocity is the rate of change of displacement, which is the same as saying it's the change in displacement with respect to time. So we can rewrite this as v equals ds over dt, right? So now we're going to do kind of the same thing. We're going to multiply both sides by t, and we get v dt equals ds. But we can't integrate this just yet because the value of v depends on t, as we found out up here, because v equals u plus at. So we can't actually integrate that until we take into account that it depends on t. So we can really only integrate constants and t's. So we can rewrite v as constants as t's, because we know that v is equal to u plus at. U is constant, the initial velocity won't change depending on time, because it's just the starting velocity. And then acceleration, we said it's going to be constant, and then there's a t. So we're going to replace the v with u and plus at so that we can integrate it. So we can say that u plus at times dt equals ds. So now we can integrate both sides, because this is just one ds and one is a constant. So we can do the integral, and we're starting, the initial time is 0, as we said, and the final time is t, of u plus at with respect to t is equal to the integral, and now the displacement, it starts at 0, because the displacement from the initial point is going to be 0 at time 0, to some displacement s of ds. So now we integrate, so we get the integral of u dt is just ut, plus the integral of at with respect to t is at squared over 2, and we are evaluating this from 0 to t, and that's equal to the integral of ds is just s evaluated from 0 to s. So now we plug in the limits of integration, and we get ut plus at squared over 2 minus u times 0 minus a times 0 squared over 2. And that's equal to s minus 0. Lots of zeros, they're just going to cancel. We get u plus at squared over 2 equals s. And then we're going to make s the subject. We're just going to rewrite it so it's kind of easier to look at by the conventions. S equals ut plus, and then by the conventions, instead of writing at squared over 2, we write a half at squared. It means the same thing. And that is our second equation of motion. For our third equation of motion, we're going to look at the fact that acceleration equals the change in velocity with respect to time, as we did for the first equation. So we're going to say acceleration equals dv over dt, the change in velocity with respect to time. Now, we're going to multiply top and bottom of the fraction by ds. It's technically not a fraction, but we can treat it as a fraction. So we get a equals dv over dt multiplied by ds over ds. Okay? And now, since multiplication is commutative, we can rearrange these terms. So we can group this ds with this dt, and then we'll have this dv and this ds. I'm going to put them in green, dv and this ds. So we can write that a equals ds over dt multiplied by dv over ds. And now we know that ds over dt, we said earlier, ds over dt is just v. So we can replace this ds over dt with v. So we get that a equals v multiplied by dv over ds. So now we have a new differential equation that we can solve. So if we multiply everything by ds, we get a ds equals v dv. So v and the dv, that's going to work because we're integrating with respect to v, and a is a constant, so we can integrate that too. So we're ready to go. Say the integral from the initial displacement to 0 and the final displacement is some displacement s of a ds equals the integral from initial velocity u to final velocity v of v dv. Okay? So now we're just going to integrate. So the integral of a ds, the integral of a constant, that's just going to be as, evaluated from 0 to s, is equal to the integral of v with respect to v is v squared over 2, evaluated from u to v. So now we're going to plug in our limits of integration. We get as minus 0, well, not minus 0, technically it's minus a times 0, which is minus 0, equals v squared over 2 minus u squared over 2. So since we have over 2 here, we're going to multiply by 2 to get rid of the fraction. We get 2as equals v squared minus u squared. And now we want v squared to be the subject, so we're going to write v squared equals, adding u squared onto both sides, we get u squared plus 2as. And that is the third and final equation of motion, at least that we're going to talk about.